Let us solve problem in fluid mechanics and kinematics. See here, a ball of relative density 0.5 1 by 2 dropped from height of 20 meter into a lake. Calculate the maximum depth to which the body sinks before returning. That means here we have to assume this is the lake surface. This is the lake surface we are assuming. Now we are dropping the ball from here. This height we given that 20 meter. Height is given 20 meter we take. Now here only gravitational force acting. In lake as it falls, this is the lake. When it falls in the lake, here two forces will be acting. One force is gravitational force, another force is buoyancy force. As it falls here, here one is gravitational force will be acting, another force is buoyancy force will be acting. Since they are asking maximum depth it will goes and return back means so sure after entering into the lake it has to move in retardation motion. That means it will come to rest where it returns. Here initial velocity we take as a 0. Here final velocity certain amount will be there. This final velocity will be taken as here initial velocity u dash equal to v we assume. At last final velocity here v dash equal to 0 we assume. Now here acceleration, we know that here acceleration is equal to g, we know. Here we have to find acceleration, a dash we assume. After finding acceleration only, for how much depth this ball goes down, we can find. First, to find final velocity here, we know the formula. What is the formula means? V square minus u square is equal to 2as. We take initial velocity 0, so final velocity v square is equal to 2 into a equal to g. Her s is given 20 meter, height is 20 meter given, and g we can take as a g taken as a 10. So 2 into 10, 20, 20 into 20, 400. Now we are going to take root, so that v is equal to we are getting 20 meter per second. We are getting 20 meter per second. We are getting now as it enters into the lake. Their initial velocity u dash we are taking as a v, that is equal to 20 meter per second. We are taking final velocity v dash equal to 0. Now after finding acceleration only, how much depth it sinks we can find. To find acceleration, what we are doing means here net force F is equal to we are taking as a mg minus buoyancy force. We know that buoyancy force formula is here we take buoyancy force. Buoyancy force is equal to V into sigma into G. Sigma is density of water. And the density of ball is rho we assume. Density of ball by density of water is given 1 by 2. From this we can get sigma is equal to we can get as a 2 rho. Sigma we can get as a 2 rho. The density of water is twice the density of ball we can get. And here if you substitute buoyancy force is equal to V into sigma is 2 rho. So 2 rho into G. V into rho, volume into density is known as mass of the ball. Mass of the ball is equal to volume into densities. So that volume into density we are getting. Volume into density is mass. So buoyancy force we are getting. Buoyancy force is equal to this 2 is we are taking as a 2. Volume into density we are taking as a m. And G, volume into density of ball is mass of the ball. So now we are going to substitute here. Force is mass into acceleration. Here mg we are substituting. Buoyancy force we got 2mg we are getting. By cancelling m, we are getting acceleration equal to g minus 2g is minus g. That means it moves with retardation minus g. Minus g retardation it moves. Now see here, from this point to this point we are taking, from this point to this point, if you take inside the lake, if you take v dash square minus u dash square, final velocity square minus initial velocity square equal to 2as we are getting. V dash is 0 minus u dash square is equal to 2 into a is minus g. This s is known as depth to which it moves down. Now see here, this u dash square how much means u dash is 20, so 20 square, this minus minus we cancel, so 20 square is equal to 2 into 10. Here d is there. If this 2 into 10 120, this 20 120 cancel, or 20 120 cancel, so that d is equal to we are getting 20 meter. That means this ball we are dropping, this ball is moves 20 meter depth before coming to rest.